injury is on the menu for today. And so let's, because you fall in lazy over break, let's remember finite injury for a bit. Okay, so what do they have in common? Well, the basic, or part of the basic outline between finite and infinite injury is exactly the same. That is, you have this collection, infinite collection of requirements that you somehow came up with, and that in most cases, if you just satisfy these requirements, then you prove the theorem. And then, right, they're ordered in the order type of the natural numbers. And then we had these requirements. They had certain actions that they needed to take. Enumerate this element into that set, enumerate this element into some other set, and they had certain restraints that they imposed on some sets. So some requirements would say, I want to restrain this initial segment of A so that no other requirement should enumerate anything into this initial segment of A, and then the order of the requirements indicates which of these restraints need to be respected. And the actions of requirement RE should respect all of the restraints imposed by all of the requirements that come before it. It's a pretty reasonable explanation of sort of the general idea of finite. Oh, and then finite injury. Most of these finite injury ones have that every requirement takes only finitely much action. And then you do this kind of inductive proof, where you say, okay, here is requirement RE. By induction, assume that all the requirements to its left act only finitely many times and have that are restrained stabilized. Then you have this particular time t, which is the time where everything to the left, all the requirements to the left that will act, have acted and have finished acting and are completely satisfied and done. All of the requirements are stabilized, and then you have this kind of static situation. Static in the sense that you now know RE will never get injured again, and all of the restraints set by higher priority requirements have stabilized, and so you know exactly what the restraint is on all of the sets you're trying to fix. And if you know exactly what this restraint is, then you also know exactly where you can do your thing and act. And then actually making a finite priority argument work is to see that this finitely much restraint that's imposed on you doesn't prevent you from taking action to satisfy your goals. So that is what finite injury is about, and sort of its key strategy for proving stuff is this idea: by induction, presume everything to the left has finished acting, has its restraints stabilized, and everything is good. Then in this context, this particular requirement can act in the way it wants to, and its restraints will stabilize, and then you've made progress of one step, and therefore induction works. The base case is usually identical. Okay, that's all very wonderful and nice. But what now if your requirements are of the form like this, and we've seen these kind of requirements before. These are the thickness requirements, which say that if you look at the eth column in A, then it should be almost the same as the eth column of B. Now, if B is finite, nothing happens, but if B is infinite, Right? In this context, usually B is given to you and you're constructing A. So if B is infinite, or if some of the columns of B are infinite, which will always be the case because the columns of B will encode some sort of strictly increasing collection of degrees, and only the first one could be finite, all the other ones are infinite. So if the eth column of B is infinite, then satisfying this is really easy, except it means you have to do infinitely many things. Infinitely many times you have to say, okay, I just saw something new appear in the eth column of B, and therefore I need to stick it in the eth column of A. And now you notice immediately that our whole earlier idea that you wait for a time t where all the higher priority requirements are done acting, that idea goes completely out of the door because a single requirement can act infinitely many times. You somehow need to deal with that they can act infinitely many times. Okay, so what are some of the difficulties that arise when one of these things acts infinitely many times? Well, difficulty A is, of course, that you could have that some RE, whenever it acts, it undoes all the good work RE plus 1 did. Now, if you have these kind of basic modules, then you've lost, because they will act infinitely much. If every action here kills what RE plus 1 did, then it's time to come up with a different module. So you don't want, you need to come up with a basic module that avoids that. But then there is still another problem, and that has to do with the restraints. Let's say RES, and RES is trying to somehow restrain A. Certain small elements are not allowed to go into A, and now whenever something gets to be enumerated into an RE, so you have to avoid that all the work RE plus 1 did gets avoided. Okay, that's okay. Certainly with these requirements, if you look at them, the work of RE does not undo the work RE plus 1 has done. Right? So in that sense, there is no problem here. But now, if the work of RE makes it so that the restraint of RE plus 1 goes off to infinity. Right? In that case, RE plus 1 can act just fine, but RE plus 2 is in trouble. And this can happen quite a bit. You can imagine that you're doing some sort of length of agreement argument where maybe not so much the limit as the lim sup is being infinity. You can imagine a length of agreement argument where whenever RE enumerates something, it destroys the computations that RE plus 1 was trying to preserve, but it immediately generates new computations that give rise to, say, a longer length of agreement. So it keeps on destroying computations. So the length of agreement RE plus 1c is entirely unstable. The computations involved in this length of agreement have, right, if they keep changing all the time, they have nothing to do with the computations that will eventually be done, because the computation that eventually gets used needs to stabilize at some point. But every time it enumerates, it could do something with this limit of this length of agreement and make it go on. Now, I changed it from lim to lim sup because this is something that often really happens and is mostly unavoidable. Well, if that really happens and is mostly unavoidable, then yes, okay, then it seems like we lost, because RE plus 1 doesn't get to act if this limit gets very high. But you're still okay, as long as you make sure that the lim inf is finite, right? If the lim inf is finite, then the restraint every now and then might get larger and larger, and say you cannot enumerate into this very large part of A, but every now and then it drops down to some very small fixed low value, and at the time when it drops down, the next requirement can quickly act and stick lots of things into A, and then later, okay, the restraint goes back up, but if it goes down often enough, then you win. Well, you need to do a little bit better than this, because if you have two restraints, both of whose lim sups are infinite and whose lim infs are finite, you still might lose, because, okay, individually they fall down, but maybe there's always one of them which is very large. And so what you need to do is you need, I think commonly you then take like the capital R, which is the maximum of all the restraints before at this time. You need that they jointly keep falling back down to some nice finite value, because then if they jointly fall down, at such a time when it's down, RE plus 2 can act and quickly stick lots of stuff into the set it wants to, and you win like that. So this is going to be our goal to achieve, that we come up with a construction where in fact we will be doing thickness requirements like this, and then we want to come up with a construction that, okay, we don't care about the lim sup of this thing, but we do care deeply that the lim inf of the maximum of these restraints is finite, and if that happens, then you can now imagine, at least on some fuzzy abstract level, you can now imagine that these kind of requirements can win. Because, okay, what is this lim inf, this finite initial part you can't touch, but everything beyond that you can touch every now and then, and as long as you act when you can, you win. Okay, and the way we're going to achieve this is going to be by the method, or sort of the idea of through stages. Right? You remember that a true stage was one. Right? A true stage of A is one where you enumerate an element into A. Let's call this little a. And now the initial segment determined by this element is already in its final state. Right? So a true stage was one where A gets enumerated into A, but then at this stage, so this is at stage S, AS up to A is equal to A up to A. And so now you can see that we know that for a CE set, for any CE set, there are infinitely many such true stages. And if you look at a true stage and you see a computation whose use is bounded below by this A, well, that computation is going to be a computation that preserves itself. Now that gets to be preserved by the whole construction, because it's a true state and nothing bad happens. Okay, I should introduce this notation just. So this uses two things. I'll make this definition precise. So AS is equal to what does this say? I wrote it like half an hour ago. Oh, let's see. The least x that just appeared, if there is such an S, Right? It's the least new S. Now, of course, in most enumerations you would pick for CE sets that will only appear one at a time. So it's the one new S that appears. Or in this S, if nothing new showed up just now. So this is AS, and then we define this set T of true stages to be the set T such that A up to AT is equal to AT up to AT. And the trick now is sort of a key trick in the particular work we're trying to do is the so-called hat trick. So I'm going to define phi hat. The hat is the new part. This is the computation from AS E going for S stages of X is defined to be undefined if there exists a Y less than the use such that Y just appeared, and otherwise it is the old computation. So this is exactly the standard Turing functionals, except every now and then you purposefully make them undefined for a step. Right? What happens here? If there exists a Y less than the use that just appeared, well, maybe there wasn't a previous computation to ruin, but if there was a previous computation to ruin, the current computation we would get now would be different, right? Or could be different. I guess I'm saying Y as less than the use. I'm not saying Y actually was used. But we don't care about such details because it turns out this is good enough. If whenever there is a danger that this computation is different than the computation we had the stage before, we make it undefined for a stage. So this is the so-called hat trick, and of course you have a hatted use as well, and the hatted use is the ordinary use if it converges, and it's -1 if it doesn't converge. So why is this the trick that works here? Well, because if you have, and I'm going to prove this, I'm probably going to actually prove this on Wednesday. I'll probably give the same proof I'm giving now, but anyway. If you have a true stage at which this hat computation converges, right? What happens if you have a true stage at which this hat computation? Well, at a true stage, the last thing that was added is a lower bound on any later things that will be added. Right? And the last thing that was added, because the hat computation does not diverge, the last thing that was added is greater than the use of this computation. And that means that this computation, as you see it now, or this hatted computation, as you see it now at this true stage, it is never going to be ruined because nothing gets enumerated into its use. So the whole use is exactly as it will be from here forever out. And so hatted computations that converge at true stages are true computations. Right? These are the computations as they will appear at the end of the construction. Of course, in your construction you can very easily use these hatted computations because everything's computable here. Right? Checking whether something just appeared is a computable kind of thing. And again, knowing what the true stages are is definitely not a computable kind of thing because it's only computable if A is computable. Okay. Good. Okay, let's do some real work then. So I'll start by giving you a theorem that shows that we need a certain lemma. This theorem is not the most interesting theorem this lemma is for. It's in fact one of the less interesting theorems, but at least you have something where you need a lemma, and then we'll reuse the lemma to prove some really nice theorems. Okay. So what does this theorem say? This theorem says, if we have a strictly increasing sequence, uniform sequence of CE sets. So we have this picture here, Turing degrees, computable. Here is 0 jump, and somewhere here there is the infinitely increasing sequence of CE sets. Notice that none of the DI is equal to 0 jump, because you couldn't strictly increase from there with a CE set. That does it. So now a reasonable question would be, is the limit 0 jump? Could you pick this sequence so that you make it up all the way to 0 jump? And the answer is no. Because if you have such a sequence, then there exists a CE set A such that all the DI are strictly less than this A, and it is strictly less than 0 jump. So whenever you have such a strictly increasing sequence of CE sets, it doesn't shoot up to 0 jump. But it doesn't just not shoot up to 0 jump. You have this strict bound in between, this explicit fixed specific bound in between. Right? You can bound it away from 0 jump.
Does that mean it's uncountably many degrees?
Pardon?
So uncountably many degrees?
We already know that, but I don't see how that follows from this.
Well, you,
There are countably many DIs. They're all distinct.
yeah, and every count sequence is bounded.
Every countable sequence is bound. But why do you already know there is uncountably many degrees?
You have countably many distinct sequences.
It's just cardinality.
The cardinality, right? Every degree has how many sets in it?
Countably many.
Countably many, because
There's only countably many terms.
there's only countably many Turing machines. And so anything in any Turing degree is equivalent to a given set in there, and this equivalence needs to be given by Turing machines. So any degree contains only countably many sets of natural numbers, and there is uncountably many sets of natural
How
numbers.
about this then? There's a linearly ordered uncountable.
Pardon?
Is there a linearly ordered uncountable string? I mean, a well-ordered uncountable string of CE degrees.
Never considered the question before. I'll think about it.
Well, yeah, I don't know.
But this is just below 0 jump, right?
Yeah, it's always below 0 jump. I don't know.
But the bounds you get from this might be the same if you throw an extra.
Oh, absolutely, yes. This A doesn't need to be injectively determined by the DI. I'll prove it to you that this is true. And then I'll think later about your question, which you might have to explain to me a little bit better before I can actually answer it. Okay, let's prove this. So actually, I'm not going to prove this. I'm going to prove that there is a certain lemma which would prove it. What happens? Okay, we have this uniform sequence. What does it mean for the sequence to be uniform?
How can I ask? Yeah, what do you mean?
That would have been a very good question, right? A sequence of CE sets is just an arbitrary sequence of CE sets you showed me. A uniform sequence is one that is given by a function h. So this means that we have a function h such that the degree of, did we have a notation for the degree of? Probably square brackets. Is di, right? There's this computable function which gives us an example of a CE set in each of these degrees. That's what it means to be uniform, right? It means that the sequence is given to you in an effective way. Otherwise, maybe this is where your counting comes from, that, right? Because this shows that there is only countably many such sequences. The non-uniform sequences, you might have more, but there is only countably many such sequences because each such sequence is given by a Turing machine. Does that answer your question?
You know what I was thinking? I was thinking any function from omega into omega 1 is flattens out, right? I'll talk to you about it after class.
Sure. Anyway, this is what it means to be uniform, that you have these sets. And why does it matter a lot? Well, it matters a lot because a key step in the proof is to now use this H to define a set B such that the wide column of B is those sets X, Y, such that X is in W, H, Y. Right, and this we've seen before. This is just take each of these countably many sets you're given here, and put the ith set you're given here into the ith column. Right? And clearly, because h is given to you effectively, this set now is the CE set. Right? To decide if x comma y is in there, you first compute h of y, and then you have the index of the Turing machine, and then you check whether the h of y the Turing machine holds on x. If it does, it's in there. If it doesn't, it's not in there. So this is, because of the uniformity, this is now a CE set. And if finally I define C to be zero jump, right? The halting problem. Maybe I should define it K. I don't know. Will I define zero jump only on degrees or on sets? Yeah, either way, you know what I mean. So now notice that C does not Turing reduce to B less than E for any E. Right? The first E columns of B consist of the first E sets from the sequence, and the rightmost column of this first E is the most powerful, and it is not up to computing zero jump. So any initial segments of the columns of B does not compute zero jump. But it's certainly possible that all of B computes zero jump. Right? That's why B is not the answer to this question, because all of it together might compute zero jump. I don't immediately have an example, but I think you could probably come up with an example that an example sequence like this that would do that. So this is exactly where we want to do our work. We want to make a set which in many ways is similar to B, but does not compute zero jump. So what we want is a set A, which is CE, such that W H of X Turing reduces to A, and C does not Turing reduce to A. Right? So a set A, which is similar to B in that it computes all of the columns here, but it doesn't compute all of C. And that way of introducing it, I hope it makes it clear that what we're going to do is, or what you want to do, is take B and massage it into a set A which works. Okay. So this exactly follows from the thickness lemma. And of proof. I told you I'd give you a lemma. The thickness lemma says, what does it say more exactly? I'll actually give it to you. Okay, thickness lemmas. If we have a C, which is CE and non-computable, like zero jump, but it doesn't necessarily have to be zero jump. If we have a B, which is CE, such that for every E, C is not computed from the first E many columns of B, which nicely enough is also exactly what we had over there. Then there exists a CE set A, which is thick in B, such that A is Turing computable from B, and C is Turing computable from A. That's what it says in my notes, but I'm pretty sure. But this lemma, with it not being reducible, makes it a lot more applicable to what we were doing over there. Right, so this exactly take these ingredients you have over there, and the output is a CE set that doesn't compute C. And because of the thickness, right? What did it mean? A is thick in B means every column of A is almost equal to every column of B. No, that's not. For every column index, that column of A is almost equal to that column of B. I suspect that's probably correct. Otherwise, you know what I mean. So now you start seeing things getting together in order to prove this theorem, which is nice, but not the key theorem we're trying to prove. In order to prove this theorem, we want to construct a set A which is CE, thicken another one, such that something else happens. Now the nice thing is, so this thickness, we know exactly what to do, right? The ETH thickness requirement, whenever it can, and it sees something appear in the ETH column of B, you stick it in the ETH column of A. Right? This is the obvious way to try and take care of thickness. And you also know how to take care of this non-Turing reduction, because we've done similar theorems like this before, where something didn't reduce, and this was through a length of agreement argument. What you try to do is you try to preserve the length of agreement, but now if the length of agreement goes off to infinity, then you can compute C from all the other information you have, but C is okay, so it'll be in that case, if C is complete, you could compute C from all the other information you have, and then the completeness prevents that because you don't have complete information. So you notice here there's this just being non-computable means we maybe need to be a little more careful. It's right here, right? The first eth columns don't suffice, so if the eth length of agreement goes off to infinity, then the first E columns would suffice to do the computation. That's exactly the argument as we did it before with length of agreement. So it seems fairly hopeful, right? We have basic modules for both of these things. The unfortunate thing is just that some of them act infinitely much. And we know that some of them act infinitely much. That means that this length, the soup of this length of agreement could go off to infinity, even though the inf of the length of agreement would be bounded. And so we need to get a handle on this length of agreement to make sure that if you look at finitely many length of agreements at a time, that all of them drop down at the same time far enough. Okay. So what did I say? Requirements. PE. The eth column of A is almost equal to the eth column of B, and NE, which says the eth Turing machine does not suffice to compute C from A. I think these obviously are the right requirements to work with. Everybody happy with these two? Right, that's P altogether makes it thick. NE altogether makes it uncomputable. Well, there's this one more thing here. Hopefully this one more thing will just drop out of the construction, because I certainly didn't stick it into the requirements. Okay, then I'll just give these definitions and then call it a day. Length of agreement is, well, the usual length of agreement. No big deal there. But like I said before, if we just use length of agreement, we run into some trouble, because there might be constantly existing fake computations that keep on going. So we need to modify this a little bit. This is the modified length of agreement, and the modified length of agreement is the maximum of those x such that there exists a stage before where the length of agreement is bigger. And now you should look at this and be a little bit how do you say, this is not new. We saw, I didn't finish the definition, but this definition, exactly as it is here, we saw once before when we realized, okay, if we're just doing length of agreement in these constructions we did, they worked fine for CE sets, but if we were dealing with delta 2 sets, things would go wrong, because the length of agreement would go back and forth, and the set could, the set we're diagonalizing again could change away and then change back later. And that's exactly why we had this kind of length of agreement before. And here we need the same trick, but then also we want to say, okay, we want to preserve any length of agreement that we have seen at any time before, if we don't have clear reason not to believe these computations. So what does it mean? Well, if it is the case that for everything less than this x, uy is equal to a up to uy, where now uy is the AUs at this stage B. So this tells exactly that we want to preserve all the length of agreements we have ever seen, as long as we don't have good reason to believe that these computations have become invalidated. And then once you have this, the restraint functions are exactly the obvious ones, right? The restraint function for E is the restraint that preserves all of these computations that have been stable since they were evolved into a length of agreement, so the maximum of all these uses. And then the capital R restraint is just the maximum of all previous length of agreements. And that's just because we want a convenient way to say all of the previous ones dropped down at the same time. Okay, I can actually finish this off by now giving you the construction. Well, finish this off is a strong word because I haven't proved anything about this construction. But A0 is going to be empty, and whenever you see an x in the eth column, x appearing in the eth column, minus as, right? I almost wrote bs here instead of as, which would definitely not work. But whenever you see such an x, and it is the case that this x is greater than the eth restraint at our current stage, then x goes into the eth column of s plus 1. So this is exactly the basic modulus I suggested it before. Whenever you see an x that you should want to put into the eth column, if you're not explicitly disallowed from putting it in, you put it in. And so what was this reason for this opaque comment about AS versus BS here? Well, you cannot take an x, see it appear, and put it everywhere where you'd want to put it, because you might see it appear at a stage where all of your restraints are temporarily very high. And so what this does is exactly saying, for any x which has already appeared in B, but is not in A yet. So this could be an x which appeared a million stages ago, but the restraint has just been too big since a million stages ago. And now finally the restraint has dropped far enough and you stick x into there. The construction works.